All right, welcome everybody. We're going to get started in about a half minute to a minute, something like that. So thanks for joining in today. I know it's challenging out there in the Metroplex, especially. Oh, good. I see Lina's back from the green room. Lina, just make sure that you can unmute your mic and so forth. And
yes.
Okay, good. Excellent. I'm going to wait another 30 seconds or so, just in case people are dialing in right now. But I think we're seeing evidence of the suppressed attendance because of the power outages in Dallas today.
That makes sense, yeah.
All right, well, I'm going to stop sharing and I'm going to go ahead and get started on the introduction here. People know that I talk for 2 minutes before these things too, so they might just be dodging me as well. Let me begin by welcoming everybody back to the SMU Physics Department Speaker Series for Spring 2021. Although I think we all agree it's hard pressed out there to feel like spring today at all. We are continuing our February series, however, and its theme of probing the unknown. But as I've just hinted, I would like to acknowledge the extreme cold weather that Texas and other parts of the country are experiencing right now, and certainly apologize in advance if power outages, which are occurring on a rolling basis right now, especially in Texas and in the Dallas region, do cut short this event. So Lina, has nothing to do with you and everything to do with the power regulation body in Texas if we all get cut off, okay? Now, in a moment, I will introduce our speaker, Dr. Lina Necib. But before we do that, I just want to remind our general audience on Zoom that to ask a question, because we've got the microphones locked down for this, just type the word speak in the chat window just to indicate that you want to speak. And I will interrupt the talk at the next opportunity, the end of a slide, to go to your question. And because we've got the mics locked down just to prevent the talking over everybody effect that happens in a Zoom meeting, you'll only be able to speak when called upon by a moderator, but then you should be free to have a dialogue at that point. The event is being recorded and simultaneously live streamed on YouTube. So without further ado, let me introduce today's speaker. So Dr. Necib came highly recommended to us today from two faculty in our department, Dr. Crystalline Smith and Dr. Jody Cooley. She received her bachelor's in physics and mathematics from Boston University before heading just over the river to MIT for her graduate studies in theoretical high-energy physics. And she went on to earn her PhD in 2017. She then headed to the West Coast for prestigious postdoctoral fellowships at both Caltech and UC Irvine before taking her current appointment as a fellow at Carnegie Observatories. And she will join the faculty of the Kavli Institute at MIT this summer. Welcome, Lina. You can go ahead and share and get started whenever you're ready.
Thank you so much for having me. And I'm very sorry for the bad weather. Hopefully, dark matter is a bit of a distraction from the cold weather. Anyway, so I'm very excited to tell you about how I use stars to trace properties of the dark matter in the Milky Way and how we can relate that to dark matter detection. So the goal of this talk is how to map out the dark matter phase space distribution at galactic scales in 3 different key locations. And before I get to that, I want to really explain why galactic scales are interesting. There are 2 major reasons for that. One is our experiments are here on Earth, which means that they're largely affected by the dark matter phase space distribution in the Milky Way specifically, but also because all deviations from the standard dark matter paradigm do happen at galactic scales. So at large scales, we really think that lambda CDM is behaving more or less well, but it's more interesting to figure out what happens, at galactic scales. So today I'm going to explore 3 different examples in which I will show you why it's important to understand the dark matter in the solar neighborhood, in the Galactic Center, and Dwarf Galaxies, and how we can use stars to actually understand that better. The first example from the solar neighborhood is through direct detection of weakly interacting massive particles, or WIMPs. And this is basically the scattering of dark matter through the standard model. And this process really does depend on how fast and what is the density of the dark matter in the solar neighborhood. The Galactic Center, the example that I will be studying here is that of indirect detection, where dark matter can annihilate or decay into standard model particles that we later detect. But of course, you can see how this process is really intertwined with the density and the velocity of dark matter at the center of the galaxy. And although we can do the same thing about indirect detection in dwarf galaxies are also very interesting in understanding other astrophysical problems like the core versus cusp problem, and basically alternative dark matter models that are not, just cold dark, flat out cold dark matter might produce different observables here. And we're going to be using stars to trace the density profiles of dark matter. So let's start with the solar neighborhood. So this is from the Lux experiment. That's a xenon atom. This is a dark matter particle, properly colored. Comes in, scatters off the xenon, and produces some scintillation light. And that scintillation light is later picked up, and that's how we know dark matter is there. However, as you might imagine, the energy of the dark matter particle is really key in estimating how much scintillation light we're going to get. So basically, the rate for this process to happen is proportional to two astrophysical properties, which are the local density of dark matter, as well as the velocity of dark matter. And the reason the velocity plays a role here is you can imagine the dark matter being really, really, really slow, that when it hits the xenon, it does not give enough energy for the xenon atom to actually cause any scintillation. And that way we would not actually see any signal. Unlike the local dark matter density, which is actually a problem that has been explored for about 100 years, so even before we had like a quite clear idea of what the dark matter is, understanding the velocity distribution of dark matter was not done as carefully. And in particular, since the first paper on direct detection by Goodman and Witten in 1985, we've been kind of assuming that the dark matter velocity distribution is a Maxwell-Boltzmann distribution that peaks at about 220 kilometers a second. The way that we actually get to this Maxwell-Boltzmann distribution is by assuming that the system and the dark matter in the Milky Way is isotropic and in equilibrium. And you can understand that if there is any other structure really in the Milky Way, that would defy such simplistic assumptions. This is why we need to build an empirical velocity distribution of dark matter. And by empirical velocity distribution, we really mean the velocity distribution, not just in the Milky Way, but really, really in the solar neighborhood where our experiments are, because we might actually have, streams or kinematic substructure for dark matter very close to us that will affect our experiments. So with that, we have a 3-step program where from simulations we can use the stars to correlate their velocities with that of the dark matter, as I will show you. Then from Gaia, we can actually go and measure the phase space distribution of these stars, and then put one and two together to end up with a local phase space distribution of dark matter. So here, the idea is to kind of like build the puzzle with tracers. So basically try to figure out when the stars are traced by the dark matter, when the dark matter is actually traced by the stars, and then use those stars as a hint for what the dark matter is doing. So first of all, if we were to take a look at one of our Milky Ways in a simulation, and this is part of the FIRE simulation, we would actually see that it has a lot of structure. The main halo is going to be sitting here, but there are also, for example, a lot of these overdensities that we call subhalos. And this is a map of the density of dark matter. If we were to take this map and overlay the stellar density map, actually of the same galaxy, we will see that there are some overdensities that will match in the dark matter on the stars. Not all of them, but some of them. So what I'm going to be discussing today is not about this physical correlation about where the stars are and where the dark matter is, but basically applying the same idea for velocity space. It's just that this is easier to visualize. So the way that you should think about it is that you have the velocity distribution, and where it's going to be stacked from different components. As you can see here, like we have the old halo, which is like the relaxed, basically the dark matter and the stars that have merged in a very, very long time ago. And then newer mergers, and then more recent mergers. So now I'm going to argue for the correlation of each one of these separately. Let's start with the old halo. So using our simulations, we can look at the velocity distributions of particles from the dark matter and the stars that have merged in prior to redshift 3, so were created prior to redshift 3, but this is their velocity distributions in the solar neighborhood today. And this is in galactocentric spherical coordinates, Vr, V theta, and V phi. We're plotting the stars and the dark matter that have merged in a long time ago, and this is their velocities today. Two things that we need to point out here. One is that they actually match and they're well correlated, which is interesting. Two is that they're actually Gaussian distributed with more or less the same dispersion, which means that if you put them together, you'll end up with something very close to a Maxwell-Boltzmann distribution. So the reason that the stars and the dark matter might end up with similar distributions is really because if you assume that dark matter is cold, which means that dark matter, just like the stars, they're both collisionless, and because they merge from the same objects, they have the same initial conditions. So you have two objects that obeying just gravity and coming in for the same initial conditions, it makes sense they would land at the same place. Then we can actually see and use our simulations to figure out more recent mergers. And we can see that, yes, we don't have the beautiful Gaussians anymore. We have more complex structures, but in using simulations, we actually see still a match between these structures and the velocities of these structures. And then interestingly enough, when we go into data, we see the similar structure. Here, I would like to pause and actually show you what the structure really looks like because well, simulations are cool. So for that, this measurement has been done with Gaia. And Gaia was launched in December 2013. It's a space telescope with the goal of giving us the positional and kinematic measurements of 1 billion stars. Actually, the latest Gaia data release gave us 1.8 billion stars, which is quite incredible. And that's about 1% of the stars in the Milky Way. The second data release, which was released in April 2018, and this is mainly the results that I will be adopting in this talk, cross-match that with 7 million radial velocities, which means that we have 1 billion stars, we have their proper motion, their velocities in the perpendicular plane, and out of that subset, 7 million will have 6D velocities. So what does this event that is very unfortunately called the Gaia Sausage actually look like? If this is the sun and this is the Milky Way, the sun is definitely not to scale. This is the merging event that is called the Gaia Sausage or the Gaia Enceladus. So what happened is that this merger, which is somewhere between 1 and 10% of the size of the Milky Way, merged in, as we've discovered back in 2018, only 2 years ago, really. It merged in at sometime between 6 and 10 billion years ago and left a trace of a lot of these stars that are very different chemically and kinematically from the stars of the Milky Way. These are the stars in red. So if we were to take a look at the motion of these stars and motion of the stars in simulations that resemble this merging event, we found that there are very good tracers for the dark matter.
So Lina, I don't want to make you spend too much time on this particular issue, but I mean, to be honest, this is the first time that I'm a particle physicist. This is the first time that I've heard that there was a merger event at all into the Milky Way. So what was this thing? Was it a dwarf galaxy or something else?
Yes, so we think it was another dwarf galaxy. That makes it sound small, but quite a larger galaxy, about the size of Large Magellanic Cloud, either somewhere between the small and Large Magellanic Cloud. So okay. It's quite huge.
So it would have been tens of millions, hundreds of millions of stars?
Yes, so it was the stellar mass is between the current estimates is between 10 to the 8 and 10 to the 9 solar masses.
Wow. Okay.
Yeah, and this is in stellar mass, not in full halo mass. That's
Great.
right.
I've already learned so much already. This is great.
So, and it's interesting. The interesting thing is that it's such a large event, and we didn't know about it until 2018, which is quite disappointing. And it's mainly because we now have the catalogs and we have the telescope power to actually see events like this. And the interesting thing is that when you see it in simulations, we found that we can draw this parallel between the structures that we have and the dark matter that actually accompany these galaxies. And it will affect the local distribution of dark matter in the solar neighborhood. One thing that I will get back to later is that there are also streams that we actually also explored with this new data set, and in particular Gaia DR2. And the cool thing about this one is that I found it, so I got to name it. So it's Nyx, after the Greek goddess of the night. And it's about 250 stars that in the solar neighborhood that are actually going in a very coherent motion. And we will go back to this one a little bit later. So what do I do about the empirical dark matter velocity distribution? Well, the speed distribution is going to have a component from the very old stuff, the halo, that I'm calling halo here, and the substructure, or the Gaia sausage, that very large merger that I just showed you. So if we were to take a look, the speed distribution, so we're not into components anymore, the Gaia sausage is going to look here as this blue distribution. The halo is red. You put them together with some errors and everything, and you end up with this solid line. One very important fact here is that the Gaia sausage actually corresponds to about 70% of the non-disk stars in the solar neighborhood. However, these mergers, because every object has a different mass to light ratio, that doesn't mean it corresponds to 70% of the dark matter. So to figure this one out, we had to do a bit of gymnastics to go from the metallicities of the stars and use the mass metallicity relation, and then use another empirical relation that basically correlates the stellar mass to the total halo mass from current observables to kind of do the jump from the chemical properties all the way to the mass to light ratio, which is why it has quite large errors, because we don't really know that one that well. Either way, this new distribution, for example, is actually quite different from the Maxwell-Boltzmann distribution that I discussed in the beginning, and especially at the tail, which I'm showing here in dashed gray. Just to be clear, I'm not claiming that this distribution is the end game, because it only includes, first of all, it only includes the Gaia sausage as part of the kinematic structures that we have. Second of all, one large caveat is that there are smaller objects that we're going to call dark subhalos that will not have star companions, so this would fail. But what I would like to illustrate now is that even it is basically the impact of changing the velocity distribution to direct detection. So this is going to affect direct detection limits. It impacts different experiments differently because, as experimentalists know, that you have a different minimum velocity depending on the material that you're using for your direct detection. It is different for different operators. This is what kind of interaction between the dark matter and the standard model that you have to assume. And of course, it also affects yearly modulations. But I will focus just on the first one. So, as we said earlier, direct detection is basically dark matter scattering off the standard model. And imagine that we have one distribution. So here in solid is the new empirical distribution that I was showing you earlier. And in dashed gray is the standard halo model. The rate here depends on the integral of f of v over v starting from a minimum velocity, which really depends on the experimental threshold and the dark matter mass, which is basically, it really relates to the minimum energy that dark matter needs to have to kick off whatever material you have above threshold. For xenon, as an example, for a 10 GeV dark matter, the minimum velocity is 567 kilometers a second, which means that if I was doing this integral, I'm going to start integrating from here on out. If I first assumed the dashed gray distribution, and then I realize, oh no, this is not the right distribution, this is the one I would like to assume, I will find that the limits that I had originally thought of would be overly constraining. However, for 100 GeV dark matter, the minimum velocity is 95 kilometers a second, which means that you can see here, you're integrating both these distributions and there isn't much of a difference here, so you're not going to end up with much of a difference. So what I would like to point out here is that this, if you change the velocity distribution, this is not an overall rescaling like it would be for the dark matter density, but it's actually, it affects different parts of the parameter space differently. So for example, in the exclusion plots that you usually are used to seeing, if this is the x-axis, the dark matter mass, and the y-axis is the dark matter scattering cross-section, if I were to assume if I were to initially assume the maximum Boltzmann distribution here in dashed gray, and then I realize that I have a different distribution, I might actually go from this dashed line to this black line right here. So the largest changes are going to happen at the lower dark matter masses.
So again, the effect of this is that you should have excluded more than you did. Am I reading that right?
So you ended up
no, you exclude less
more than you should have. Yeah.
Okay, right. You over excluded. Okay, right. You said you over excluded. Okay, got it. That makes sense.
That's right. So basically, it's not the most conservative strategy. Okay, so beyond that, what I would like to explore is actually really these new streams and how they would affect the local dark matter distribution. So Nyx here is a Greek goddess of the night, and what I would like to show you is really its distribution in velocity space and in position. So let's kind of like go through these panels one by one. Starting here, so this is Radial Velocity Vr, this is V5. The stars in the disk of the Milky Way are going to be rotating at about 220 kilometers a second, which means that they will be around here. They don't really have a radial velocity, which I usually think about as like kind of like a breathing mode or something. But they will have a non-trivial rotating velocity of V5. The Nyx stars actually also are on prograde orbits, which means that they're also co-rotating with the Milky Way. However, they have a non-trivial radial velocity. This is quite unusual, and the reason that nobody had seen this before we kind of got to it in 2019 using machine learning techniques is because it's basically buried under the co-rotating disk stars, which are not really related to the dark matter. If I were to take a look in position space, so this is X and Y, this is the plane of the Milky Way. All the stars have the same motion and they're kind of all going this way. The vector here for the sun is actually exaggerated just so you can see it. But if we were to overlay the picture of the Milky Way, it would look like this, where the sun, which is a very it's a very lame star. I probably should not say that in front of astrophysicists, but it's a very young disk star, and it's going to be co-rotating. The Nyx stars are actually going to be in a kind of going into a perpendicular motion. So they have a prograde rotation, but also going inside or into the Milky Way. Same thing if we were to look in the opposite plane, so X and Z, you can see that these stars actually extend a little bit above the disk of the plane, or at least like above the thin disk of the plane.
So Lina, just a question. Are any of these Nyx stars that people would be familiar with? Like, what's the closest Nyx star, for example?
Oh, so we cross-matched this with, I mean, they are pretty close. So a few of them are they're pretty bright and at a few hundred parsecs. So the first thing that we did when we found these in the Gaia catalog is looking at other catalogs, trying to see how much information we can find about the chemical properties of these stars. And unfortunately, very, very few have been actually measured before. And so what we ended up doing with my collaborators at Carnegie actually is we submitted, at this point, I think like 4 observing proposals 2 of them got canceled because of COVID, as you might imagine, to actually go and observe these stars. And we observed them with the Keck telescope in Hawaii, and most recently with the Magellan telescope in Chile, remotely for both. And right now, basically, my collaborator, Alex G., who is going to be starting a new faculty position in Astro at U Chicago this fall, we're analyzing the chemical properties of these stars and trying to understand the origin.
Okay, but these were largely previously undocumented stars.
Exactly. So they were not really, I mean, even though they were close and bright, but they were not on anybody's radar.
Interesting. Okay, thank you.
I thought it was interesting. So the reason that these stars would be interesting is either there are a disturbance of the thick disk, which means that the disk of the Milky Way got hit by something and knocked all these stars out of an interesting orbit, or something that would be interesting for me specifically is that they are the elements of a merger. So, because it's very hard to imagine, interestingly enough, in one of our cosmological simulations, we saw an event that kind of looks like this. So this is the equivalent of the Milky Way, and you're going to see it actually merging with a different object. So this is it, and then it gets hit by something that is Nix equivalent and kind of gets pulled into this co-rotating kind of orbit, which is quite interesting. So if it is indeed this type of merger, it would actually bring in a lot of dark matter with it, or at least dark matter on interesting orbits with it. And if it is indeed a merger, then we need to understand how much dark matter Nix is actually going to contribute. Back in 2008, there was this paper by Justin Reed et al. That says, as satellites are torn apart by tidal forces, they deposit both their stars and their dark matter into a thick disk. The latter point is the key new idea presented in this work. A dark matter disk must form in a lambda CDM cosmology. And the words here that kind of like struck with me is a must form. The reason that they actually got into this conclusion is because they looked at a lot of different simulations and realized that mergers that are going into this, more parallel fashion that gets into this prograde orbits happen quite often. Maybe must form is a little bit too strong, but they do happen. So a follow-up paper that same year actually discussed the implications for direct detection. But before that, let me actually show you, or at least have a bit of an introduction to what they found. So if we were co-rotating with the dark matter component, it means that its velocity is going to be very close to ours. So it would peak at very low velocities. So you can see if this is distribution that I actually drew by hand because I didn't want to commit to the actual distribution yet. You can see that it's not going to affect any measurement in the low mass, the 10 GeV, because you're again integrating from Vmin onward, but it's going to affect the high mass dark matter, or the 100 GeV, for example. So this follow-up paper from 2008, for example, was looking at, I think, Xenon 10 at the time. And if we were to focus on this black line, again, in direct detection plots, where this is the mass of the dark matter and this is the dark matter scattering cross-section, we see that if you don't assume that you don't have any dark disk, this is the line that you end up with. But if there is a more and more contribution from this co-rotating structure, you might end up changing your limits at the high end by quite a lot, actually, which is quite interesting. So the sausage might affect us on this end. Co-rotating dark matter, maybe from Nix or other streams, are going to affect us on this end. So at the end of the day, this whole picture, we have to be very, very careful what we're doing, and we might be on the cusp of understanding of, a new understanding of the phase-space distribution of dark matter. So of course, there's a lot to do to figure that one out, and in particular, the observational study of Nix, which I discussed, about understanding the chemical properties of these stars to figure out if it is indeed a merger just like this one. Correlating the velocity of dark matter and the stars in these streams, and estimating the relative contribution of dark matter from such objects. But also going back to the earlier caveat, is understanding the contribution of dark subhalos or mergers that really do not have, they're too small to have any stars, but they might actually affect the local velocity and density of dark matter. Before I move on to the next section, I was wondering if there are any questions.
Yeah, so if you want to ask a question, just type the word speak in the chat window and I'll get you unmuted. All right, looks like so far so good.
So far so good, all right. So as I said earlier, we had to assume that dark matter is actually collisionless for this correlation to happen. So, and interestingly enough, you can actually, I did check it, if you end up with introducing a self-interaction, this correlation really breaks in a lot of these mergers. So then we have to find different methods in understanding the phase-space distribution of dark matter in alternative dark matter models. But this is just kind of like a taster for what's about to come. Okay, so we discussed the importance of the phase-space distribution of dark matter in the solar neighborhood. We can now go into the Galactic Center. Why is the Galactic Center a good place to look for dark matter, in particular for indirect detection? Well, it has the largest density of dark matter. So if you were to see any indirect detection signal, you're going to see it from the Galactic Center first. The con, of course, is that it has large astrophysical backgrounds, or basically a lot of other things that are baryonic physics that we just don't understand as well. So the example that I'm going to show you here, this is just a case study, is basically by adding one extra dark matter particle. As a simple extension of the standard model, it's going to be at the TeV scale, so harder to probe in colliders. And let's see how it would affect our limits. So I'm using this particular example just because two of the co-authors who actually spent a long time calculating this process and these crazy loops actually were office mates of mine. So I heard them complain about it for a while. And basically, this is dark matter annihilating and into very high energy jets, and eventually actually giving us gamma rays that we can detect using Cherenkov detectors on Earth, for example, like HESS. So the rate for the signal is going to be proportional to the flux, the experimental efficiency, and of course the exposure time. So basically, the scattering cross-section, as well as, the density of dark matter and the efficiency of the experiments. So what I would like to actually kind of go through, and you'll see very quickly where this is going, is basically how much the theoretical uncertainties, experimental uncertainties, and astrophysical uncertainties do affect this particular example. For my friends who spent ages calculating this loop, their theoretical uncertainties are actually down to 10% and how much they affect their limits, which is quite incredible. Our experimental collaborators actually do an amazing job building these wonderful experiments where the experimental efficiency is basically kind of narrowing down the effect down to 25%. But not knowing the dark matter density gives us an effect of about 50,000%, which means we don't know really much. So why is that? This is because the flux of the dark matter is going to be proportional to this J factor here, which is proportional to the density squared of dark matter along the line of sight. And the dark matter density, so rho as a function of the radius, this is where we live at 8 kiloparsecs from the sun. It could be either like an NFW or an Inasto profile or a Berger profile. And maybe some of these are a little bit more likely than others, but we don't really rule them out. So the density profile of the dark matter in the Milky Way could be any of these. So much so that when we have these exclusion plots, they have to take into account a lot of these possibilities. So this plot, for example, on the x-axis, we have the dark matter mass. On the y-axis, we have the scattering cross-section, the theoretical scattering cross-section for this line process. And in gray here, we have, this is the calculated scattering process. And basically everything above these horizontal lines is going to be excluded. Let's kind of go through an example for different profiles. So if, for example, I have a core, so something like flat like this, that lasts about 2 kiloparsecs, like up to here, which is in blue, it means that I'm going to exclude dark matter masses from 2 to 3 kiloparsecs in this narrow range as well. However, if I were to assume an ionosto profile, then I can exclude everything up to 10 TeV. So you can see that the physics implications are quite different. And this is why it's very important for us to understand this density profile and really narrow it down a little bit. So the density profile, as I was mentioning, could be in NFW, ionosto, Burkert, and the goal is to really narrow that down. One way we can do this is to measure the escape velocity of the stars in the solar neighborhood, which actually helps us understand the potential of the Milky Way. And from that, we try to deduce the dark matter density profile. This is the extent of Gaia DR2, the second data release, which is unfortunately very small, so I'm not going to be able to actually do this. But with Gaia DR3, which hopefully will be online sometime in 2022, we will be able to make a stronger statement down to further distances. And this is just a kind of an example to show you how the escape velocity as a function of the distance does change as a function for different profiles, which is why we're able to use it for constraining power. So how can we determine the escape velocity? So I'm using here mock data, and basically the escape velocity, as has been done in from the paper of Leonard and Tremaine in 1990, is to basically fit this distribution and find where the cutoff is. That's the whole point. However, you can imagine that you actually have stars above the cutoff. The arrow here is the cutoff that I have of about 500 kilometers a second. And the reason for it is that either they're badly measured stars or they're unbound stars. You might actually have unbound structures, stars that are just like flying by, and then they are not going to be bound to the galaxy, which means that they're not going to be able to tell you about the potential. So what you need to do is fit this as a v escape minus v to the k, where the k is the slope and the v escape is the cutoff, above a minimum velocity to kind of define the tail of the distribution. And of course, there are a lot of complications, because that's the theme of my research, is where are the complications? And we need to understand how we take into account the errors, and a lot of people have done that, and the presence of outliers. We need to be able to fit those into a different model. We do that as well. But finally, one interesting thing that has not been taken into account in the previous literature is the presence of multiple components. In particular, what I actually showed here is actually the result of generating a distribution from the Gaia Sausage that I discussed, as well as the halo, the old stars and the old dark matter, and an outlier distribution. In the literature, it has been really for long assumed that Vmin is about 300 kilometers a second for an escape velocity in the 500 or so. So you can see that it is not really defined as the tail. And in particular, if you were to define, for example, minimum velocity as 400, you would be dominated by a single distribution and everything is okay. However, if it is 300, then you really need to model these two distributions. It's not just a single one. So you have to be very careful. The way that people have people basically in the literature before tried to do this, and they found that the escape velocity and the slope are actually quite degenerate. So the way they kind of came around that is by putting what I find artificial priors on the slope to be able to constrain this. So let me actually explain what I'm saying. These are mocks. So for example, if I had this distribution and it was actually generated by a single function, and I was fitting for the escape velocity and the slope, I will end up with I will run an MCMC, do the fit, everything, and take into account like that I have errors. So this is why it's not perfect. And I will end up with something within like a little bit less than 2 sigma. This is 1 sigma, 2 sigma, 3 sigma. However, if what I generated actually is from 2 functions and I'm fitting it with just this single one, I'll end up really, really off. Basically, my escape velocity, my best fit is really different from the true answer, which is what it is here. So the way that people get around that is by limiting the prior on the slope, so basically not letting it kind of vary as wide as it wants, and you end up with biasing your results in crazy ways that you have no control over, which is why I don't think this was a good idea. So the best way is to actually model your distributions by the right number of components that you have. So now what I'm showing you here is actually the distribution from Gaia DR2 in the solar neighborhood. And this is what it looks like if I fit it with a single component and an outlier model, just to take into account these extra stars. With 2 components, things look a lot better, even with 3 components if I wanted to, and then we'll end up with the correct escape velocity, or at least with what I think is the correct escape velocity. Of course, we use the Akai information criterion here to make sure that we're not overfitting, because of course, once you give it more functions, you can fit more things, but you need to make sure that you're not just, these functions are required. So another thing that we do is actually do this fit at different minimum velocity. And the reason for it is because we want to understand the physical kind of interpretation of this. So for example, if you are fitting with a single function, at 300, you end up with some weird very high escape velocity, but you can see it kind of like sliding down the higher your minimum velocity and kind of sticking up here. At the same velocity that if you were fitting with 2 functions from the get-go, you will end up with the same distribution, with the same escape velocity. So physically, it makes sense. The higher you go, you're going to be dominated by a single distribution, and this is what you're going to get. And here in green, I'm showing the 3 functions, just because the 2 functions is not really enough at 300, but it would be at later ones. So from these, we can actually measure the escape velocity. So this is the 3 function result at Vmin of 300. This is the 2 function result at 350, single function result at 375. And you can see that they're actually consistent. The reason that the arrow bar actually grows here in any of these is because the larger your minimum velocity, the smaller your statistics, because you're getting rid of a lot more of your data. So that's why this is kind of largely expected. And these are previous numbers from the literature that these 2 actually assume a narrow prior on K. And this one actually, Copeland et al. Measures using the proper motion, but a different radii for a much larger data set. So from that, we can actually go and have some measurements about the mass of the Milky Way. And the masses that we find are actually a little bit lower, although still not crazy far, but somewhat consistent, still lower than those of the literature. This is only the first step, because this is not really understanding the full density profile. And the reason that I'm only stopping here at the mass is because, as I said, Gaia DR2 really gives us a view into a very narrow range. So we're hoping that with Gaia DR3, which hopefully you'll stay tuned for, we're going to be able to make a much stronger statement. And now I'm going to go to the Dwarf Galaxy part, unless there are questions.
Yeah, so if anybody has any questions, again, just type speak in the chat window. Okay, press forward.
Okay, so the cool thing about Dwarf Galaxies, if you were going back to the indirect detection kind of idea, is that they have a small astrophysical background, but it's a much lower dark matter density profile. So dwarf galaxies, we have quite a few. Some of them here are actually shown in blue and some in red, and the red are the candidates. And basically, we're discovering more and more of these dwarf galaxies, which are satellites of the Milky Way, and that's pretty cool. Interestingly enough, we can use their measurements. So for example, the circular velocity of this dwarf galaxy is a function of the radius to constrain whether or not they come from a cusp or a core. The reason that this is interesting is because these objects, dwarf galaxies, don't have enough baryons to actually shape the inner part of the density profile into a core, which means that if you actually see this and there are not that many baryons, you might actually have an interpretation for self-interacting dark matter, as the self-interaction here is going to be repartitioning the energy in the center of the galaxy and taking the cusp into a core. Of course, there are a lot of complications for this process. And in particular, for example, the way that we actually use genes modeling to actually obtain it. Genes modeling is assuming, because for these, we use stars as tracers of the dark matter potential. And for these faraway objects, we only have the line of sight velocity. We don't have the 3D velocities. So to do that, we actually have to assume that the whole object is spherical and that their kinematics are actually either isotropic or there is some kind of anisotropy. So some kind of relationship between the line of sight velocity that we see and the other components. So with a student, Laura Chang at Princeton, and I actually a few months ago posted this paper where we took a very simplistic mock of these dwarf galaxies, and we just asked the question, if we put them through the standard procedure, do we get the answer that we put in? And the answer was not in all cases, which is quite interesting. The solid line here is the actual, distribution, where on the x-axis we have the distance, on the y-axis we have the density profile. And for a lot of these measurements, if you only have 20 stars or 100 stars, you're not going to be able to actually get that core correctly. But if you end up with 10,000 stars, then things kind of get nailed down properly. So what we can do is plot the posterior distribution of this inner gamma, where this is a generalized NFW profile. And if gamma equals 1, that means it's a cusp. That's the regular NFW. If gamma is 0, this is a core. And if the initial distribution is actually a core, and we vary by the number of samples or number of data points of these stars and how well they're measured, you can see that basically a posterior like this is not going to tell you anything. It's just like pretty much flat. So you don't really know what the gamma is. With high enough statistics, really you're able to actually get some concrete results. This is the same exercise, but for a galaxy. So here is 10 to the 9. This is for a 10 to the 7, so more of an ultra faint. And with large enough errors that are actually kind of very close to the velocity dispersion of your system, even with a lot of different stars, you're not going to be able to get it right. But with accurate and on a lot of measurements, it's okay. And of course, with observers, it's very, very difficult to kind of get 10,000 stars out of a lot of these systems. They're quite far away. A lot of the closest ones are, I think, at about 50 kiloparsecs. So we need to really understand, kind of envision newer strategies. And I'm talking to my colleagues at Carnegie, my observer colleagues at Carnegie, about what we can do to actually have more reliable information and results from the profile of dwarf galaxies. From the particle physics side, this actually can affect the measurements that we get. So here for the massive galaxy, the 10 to the 9 versus the 10 to the 7, when we kind of go through this exercise, we find that with a number of stars and different errors, we usually tend to overshoot, which means that we think that there is more dark matter than it actually is, unless when you have very few stars and large errors, in which case this is consistent with basically not having any dark matter. So the reason that this would be concerning is because a lot of our measurements come from a few dwarf galaxies that really dominate this J factor. This is like an order of from decreasing J factor. And which means that the limits are actually dominated by the first few. And you can see that these systems have 20, 70, 59, 37 measurements and very low dispersions, which means that your errors have to be much, much smaller than this to be able to get them right. So this is why it's really important, at least for indirect detection, to get this correctly and not take these numbers at face value, because we really have very few statistics. So we need to understand this better. Once, for example, we have the density profile of these galaxies under control, and hopefully we do, we can start exploring other dark matter scenarios. So for example, what happens with dissipation? And in dissipative dark matter models, actually, you end up with steeper cusps even than the regular NFW. While with the self-interaction, you end up with cores. So there is a large variety of what is the astrophysical interpretation or the astrophysical consequences of a particular dark matter particle physics model. And keep on the lookout for this paper. It's led by Jacob Shen, who is a Caltech graduate student. And I think he just emailed that he's going to post it on Thursday. So definitely keep on the lookout. It's a great paper. So there is a lot to understand about dark matter. And hopefully what I was kind of telling you today is that we can use a lot of these tools and the new tools about stars and the kinematic of stars to understand dark matter. So to summarize, in today's talk, what I wanted to tell you is that we can map out the dark matter phase space distribution at galactic scales using stars and with different methods at different locations. But all of these have actually quite a tight correlation with our detection of dark matter and the particle nature of dark matter. But I will leave you with the best thing that I've ever made, which is Nix coming out of the Milky Way. Thank you.
No, thank you very much. And we'll try to give you a little applause here at the end. All right. So let's go ahead and open it up to questions. And again, if anybody has questions, just type speak or something like that in the chat window, and I'll get you unmuted. While we're waiting for people to do that, I was wondering if I could ask you another question, Lina, although I've been dominating this the whole time. I actually wanted to come back to the challenge of whether or not, what happens if dark matter turns out to have some appreciable self-interaction of some kind through a dark sector or something else like that. Can we go back to, I think it was actually very early on in your talk, although feel free to pick any slide you want. It was when you were still talking about the stellar neighborhood, and you kind of made this side comment about SIDM will mess up the correlations, right? Which obviously makes a lot of sense, but I wanted to probe the degree to which they could already be messed up based on what we know. Yeah, so it was that nice plot with the two lobes versus the single lump.
Right.
Right. A few slides.
My computer has lost its mind. So
those.
Okay. There we go.
Yeah, there we go. Perfect. It happens to me too when the graphics card goes nuts.
Yeah, exactly. Here it is.
Yes. Perfect. So I know that there are already constraints on the degree to which dark matter could be self-interacting. When you made this plot on the left, which presumably is an example using some assumed degree of interaction, how much interaction did you assume, and where did you get that assumption from?
So for example, for this particular one, it's 1 centimeter squared per gram. That's the scattering cross-section. Okay. The limit from clusters is less than 1.5. Well, you have numbers at 1.5, sometimes 10, something like that, centimeter squared per gram. That, however, is not like that's if you assume that the scattering cross-section is constant for all of these objects. You can also assume that if you had like a Yukawa kind of process, just like this one, this the scattering cross section is going to go as 1 over v to the fourth, the velocity of the system. And then you can see that basically that allows you to have very, very high cross sections for smaller objects, for ultrafaints or dwarfs and Milky Way, because the tightest constraints that we have are coming from clusters.
I see. Okay.
So yes, so there are some constraints, but not a lot, is what I'm trying to say. So there's quite a huge window. And the interesting thing is that the ramifications for structure formation for a lot of these kind of local mergers and everything has not really been explored. So that's one of the things that we're going to be doing here with the dark matter dissipation and dark matter self-interaction, is basically how does that affect the phase-space distribution of dark matter locally.
Okay, but the bottom line is that plot on the left assumes a self-interaction cross-section that's already lower than typical limits from experimental constraints already.
Yeah, so for example, this one is allowed.
Right, and it's significant, right? And it really messes up the correlations.
Exactly. So you don't have a correlation between the dark matter and the stars.
Okay.
Yeah.
All right. Yeah, Junbo, you had a question. You should be able to unmute now.
Okay, thanks. I have maybe a very stupid question because I'm preparing for the lab for our entry lab courses. One of the question is if in the universe we have 27% of dark matter, only 5% of visible matter, how come we don't see the dark matter in the solar system?
Oh, in the solar system. Yeah, it's because basically it depends on the distribution. Let me try to find a good plot for this. Yeah, it depends on basically where the density of the dark matter versus the density of what we see. It actually varies. So the 27% and the 5% is just like averages over everything. Mm-hmm. And here, for example, in the galaxy, so where we are actually, if you take kind of like a box of about 1 kiloparsec, we live on the edge of the galaxy here, like about here. It's more like 50-50 density wise. And then the further you go up, the baryonic density, so the stuff made out of, the visible matter drops very, very sharply, and then you're dominated by the dark matter. So your dark matter is going to be, the dark matter halo extends by a factor of 10 to the size of the galaxy. So for example, this one is about 10 kiloparsec. The virial radius of the Milky Way is about actually 400, but you can think of it as order 100 or so. And that's where the dark matter kind of like dominates. And we just, because we are kind of attached to one of the disk stars, that's why we're dominated more by the baryonic physics.
Okay, so in that sense, then does it make any sense that we try to detect the dark matter on the Earth, if dark matter is more or less negligible in a solar system?
So that's why there are different methods of detecting the dark matter. For example, direct detection is for, you hope for the dark matter to come in and like knock off your xenon. But yeah, for example, indirect detection, which I'm showing here, is really relying on dark matter annihilating at the highest density point in the galaxy, which is going to be at the center of a galaxy. And of course, we can look into the dwarf galaxies as well, and measurements from, galaxy clusters and everything. It's just that the flux goes as 1 over distance squared. So the closer, the better. That's why basically there are pros and cons for a lot of these methods. And yeah, and you want to have them all in the hope of discovering dark matter.
Okay. Just a clarifying question related to Jingbo's point. My recollection is that if you assumed a 10 or a 100 GeV dark matter particle, and take the standard Maxwell-Boltzmann distribution and other information, that like passing through your hand every second or so, there's at least dozens, if not hundreds, of dark matter particles, something to that degree, right? It's not one a year; it's many a second that are passing through an area the size of your hand.
Yes.
Right. Something like that. Okay. So
yeah. So I think there are boxes that say, like, small boxes about like coffee cup about the rate of dark matter.
Yes.
But I don't know. Yeah. Yeah, the problem is that the scattering cross section is very, very low, or at least like we probed it down to I think 10 to the minus 45 centimeters squared per second, centimeters squared, sorry, just for, regular WIMP dark matter. So even if you have quite a few of those, very, 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 very few are going to actually interact, and you would be able to see them.
Right, exactly. So it must be extremely weakly interacting with matter, with visible matter. But is there any calculation that the possible resistance of dark matter to, let's say, the Earth, the orbiting of the Earth? Because I don't quite remember the exact number of how long solar system has existed. Do we observe any slowdown of the Earth or any planets in the solar system?
Oh, I see.
And
so
from that, do we know? Can we calculate the interaction or resistance to those motions?
Yeah, the unfortunate part of that is just gravity is very, very weak. That's why we're looking into very large objects to kind of see what the dark matter is. Like, we can talk about dark matter in the bullet cluster because of like its galaxy clusters on like 10 to the 13 to 10 to the 15 solar masses. The Milky Way itself has a 10 to the 12 solar mass halo. But like when you go into small objects, which is what the solar system is, unfortunately, within this framework, gravity is very, very weak. So it's very hard to kind of make any very strong statement about that.
Yeah. But it actually is kind of an interesting, like, upper level undergraduate particle physics question. If you imagine a certain, number of particles per cubic meter in the solar system, and each of them can interact with a proton with a certain cross section, how long would it take to slow down the Earth so that its orbit around the sun takes 2 years or something like that? And I'll bet it's a ridiculously long time, but because it's a numbers game on the cross section and all that stuff. But I hadn't thought about it that way before, actually.
Well, I didn't until this morning. I was writing this co-op question for the dark matter lab,
right.
And I got myself in trouble because I couldn't answer those questions.
Yeah, no, so the timing is perfect on this. Yeah.
Exactly.
All right, are there any other questions or comments? Anyone else like to ask a question of Lina? This has been great, thank you. Okay, it looks like not. So in the interest of wrapping things up kind of, on target, like we usually aim to do, let me thank you one more time, Lina. This has been great. And we really appreciate your time and knowledge and sharing that with us today. And I hope you continue to remain well and safe. You're on the West Coast, as I recall, right?
Yes. Thank you so much. I hope you guys are all safe and don't have any power outages and everybody's great. And
yeah, I wish that for everyone right now. So, all right. Well, on that note, thank you very much. And we'll go ahead and close the event out. Thank you.